In this video, we look at the slope of a function. A simple idea with deep and profound consequences is to attempt to treat functions as if they were straight lines. Given a point on the graph of a function, we might ask, what is the slope of the function at that point? In what direction is the function going at that point? How is the function value changing as x changes? In other words, given a curve, which might not be a line, and a point on the curve, what is the direction of the curve at that moment? This is an ancient question, and its answer has powerful applications. We will explore the applications first here, and then develop the tools over the next several weeks to find the slope of a function. The slope, that is the ratio of the change in output to the change in input, or the change in y divided by the change in x, is constant for lines, for linear functions. We're going to generalize that concept to all functions. Take, for example, the function f of x equals x squared plus 2x, and let's graph it near the point 2,8. In the large, the graph of our function is a parabola. This is obviously not a line. But if we zoom in on the point 2,8, eventually the graph of the parabola begins to look like a straight line. It begins to look like something like this, even though the graph is not a line. If we test a few points, for example 2,8 and 2.1, 8.61, take my word for it that 2.1, 8.61 is on this parabola, we see that this line has slope about 6. So the slope of the curve y equals x squared plus 2x at the point 2,8 is about 6. When we look at the slope of a function, we need to do that at a particular point. If the slope of a curve near 2,8 is about 6, then the curve looks like the line y equals 6x minus 4. Take a moment to verify that y equals 6x minus 4 is a curve with is a line with slope 6, and it goes through the point 2,8. So the linear function g of x is 6x minus 4 is a good approximation for x squared plus 2x near 2,8. Again, the function g of x equals 6x minus 4 approximates this parabola near 2,8. If we were to graph both of them on the same screen, we will have the parabola shown here in blue and the line shown here in red, and they look almost identical. The parabola curves up slightly at the endpoint, so you can see a slight change, but in the middle, near 2,8, they're the same, or almost the same. On a graphing calculator, we can approximate the slope of a function at a point by zooming in on the point until the graph begins to look like a line. And you might try that with a number of different functions that you graph on a graphing calculator. Hit the zoom button a number of times and see what happens. For example, if we wish to find the slope of this parabola at the point 2,8, we can type in the formula y equals x caret 2 plus 2 asterisk x into our graphing calculator, and then trace the graph until we're near the point 2,8. Your calculator, or I use a software package like Sage, available on the university campus, might draw a picture of the parabola like this. At first glance, it's clear this is not a line. This is a parabola. But if we zoom in at the point 2,8, our curve begins to take pictures like this. It begins to flatten out and begins to look like a line. This will be true for every function that you use in the sciences. If we zoom in far enough so that, say, the x values are between 1.8 and 2.2, we might get this image. We can do that on a graphing calculator by typing in xmin, xmax, ymin, and ymax as shown here, and hitting the graph button on a TI calculator. To find the slope of the curve near 2,8, we need a second point. So if I'm using a TI calculator, I can use the trace function and find some nearby point on the curve, such as this one. I found this one using my calculator, 1.9900, 7.9401. All right. You may get at a slightly different point. That doesn't matter. Now I have 2 points, 2,8 and this one here. And if I have 2 points, I can compute the slope between them. The slope is a change in y over the change of x, and I get about 5.91. So the slope of the curve y equals x squared plus 2x at the point 28 is probably about 6. Let's do some exercises to practice this. Suppose we have a function, may not be a line, but goes through the point 4,2, and near that point it sure looks like a line with slope 1/8. What's the equation of the line that looks like this function? And what's the y value on this line when x is 5? We'll do the first part. Suppose we have the graph of the function, slope 1/8, go through 4,2, looks like a line. What's the equation then? Well, the slope of the line is the ratio of the change in y values divided by the change in x values. So for any points x1 and y1, x2, y2, here's my slope formula. Change in y over change in x, rise over run. In this case, one point is 4,2 and the slope is 1/8. So let's plug those in. I'm going to use xy for any other point on the line so that my slope here, 1/8, is the change in y values, y minus 2, over the change in x values, x minus 4, or multiplying by the denominator, we get this. There's the equation of the line with slope 1/8 through the point 4,2. This is in fact the point slope formula I'm using here, and it's the best formula for working with lines in this class. The other question we had was, what's the y value of this line that corresponds to the x value, x equals 5? Well, a moment ago we found the equation for the line, and what we're really asking for is what is y when x is 5? So plug in. And so we get 1/8 times x minus 4 is y minus 2. Since x is 5, we get this. So y is 2 plus an 8, or 2.125. Here's another problem. I have some function, probably not a line, but it goes through the point 2 minus 1, and near 2 minus 1, it sure looks like a line with slope 4. Where does that line hit the x-axis? This is a slightly different question because I'm asking for the x-intercept of the line. Again, by the point slope formula for the line, we have that the slope is 4. The slope is the change in y over the change in x. So the numerator will be y minus 1, and the denominator will be x minus 2, or in other words, y plus 1 over x minus 2. But here we're asking for the x-intercept of this line, so we want to know when y is 0. So if we want to know when y is 0, we plug that into this formula, and we get that the slope 4 is 1 over x minus 2. Now we solve for x. And so x minus 2 is 1/4, so x is 2 plus a fourth, or 2.25. In both of these problems, we collect information about an unknown function, probably not a line, by assuming that the function acts like a line with certain slope. In the next presentation, we explore further the linearization of a function.